There we go. So a mole is a method to count a large number of atoms or molecules. Sorry, my handwriting sucks. It's kind of hard to use a mouse. Okay, so a method to count a large number of atoms or molecules. That's what a mole is. Now, the question would be, what number do we use? Do we use a million? Do we count atoms by the millions or the billions? What number do we want to use? Well, there's a not so intuitive number, but it's really amazing, and we'll understand over the next 2 weeks why this number is so amazing. But this is called Avogadro's number. It is 6.02 times 10 to the 23. That is 23 decimal places after this. So this is like billions of billions of billions of atoms. So 6.022 times 10 to the 23. This is Avogadro's number. Now write this down and box it or highlight it or do something. We're going to use this for the rest of the semester. So this is like, it's like you could count something like a dozen of eggs. You say 1 dozen is 12 eggs. Well, if we say moles, we say 1 mole of atoms is 6.02 times 10 to the 23rd atoms. It's a really big number, and we'll see, hopefully you'll start to see why this is such an awesome number. Okay, so number 2, knowing that 1 mole is always this number here. How many atoms are in 1 mole of carbon? Does anyone know how many atoms are in 1 mole of carbon? So this one, it's not a trick. So 6.02 times 10 to the 23rd. And if you're having trouble understanding what that means, that's like this: 602200000, dot 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 dot, tons of zeros. This is like billions, 23 decimal places like this. So there are 6.02 times 10 to the 23rd atoms in 1 mole of carbon. How about how many molecules are there in 1 mole of water? Well, again, it's the same number, 6.02 times 10 to the 23rd. So again, we have 1 mole. 1 mole is always the same. It's the same number no matter what. Okay. So that's one concept, is a mole is always the same. The next thing is what's called a molar mass. Now, a molar mass is, we're going to need the periodic table. So if you don't have a periodic table, I would recommend you get on your laptop in another tab or on your phone or something, pull up a periodic table on Google. Now, why we use Avogadro's number is that, let's just take an example here, like carbon. So let's take carbon, for example. Carbon has a weight, trying to explain it in terms that we haven't used yet in this class. So an atomic mass, let's call it that, atomic mass of 12.01 atomic mass units. That is, we have 6 protons and 6 neutrons, so 12 atomic mass units. So if we had 1 mole of carbon, how many grams would that be? Does anyone know, if we had 1 mole of carbon, how many grams of carbon that would be? So this would be 12.01 grams of carbon. Just say grams. So this is why a mole is such an awesome number, is because if we want to figure out how many grams there are in 1 mole, that is, how much grams would 6.02 times 10 to the 23rd atoms, how much would it weigh? We just have to look at the periodic table. It's 12.01 grams. Now this is what we call a molar mass. That is, how many grams is it per 1 mole of carbon? How many grams is it per 6.02 times 10 to the 23rd atoms? So knowing this, if you want to find the molar mass, you just grab this number from the periodic table. Let me do one example problem, and then I'm going to give you a couple minutes to try to get the rest of the molar masses. So if we wanted the molar mass of nitrogen, well, again, we just look at the periodic table. And where's nitrogen? Here's nitrogen. It has a mass of 14.01 about. So the molar mass of nitrogen would be 14.01 grams per mole. 14.01 grams per mole. We're literally just going to the periodic table, grabbing the number and writing it down. That's a molar mass. So what I want you guys to do, I'm going to give you a few minutes and try to work through the rest of these here. And just think about it. Well, if this one's 14, what would 2 of them be? So this one's 14, what would 2 of them together be? And then all we're going to do is grab the different elements from the periodic table and add their numbers together. So try to work through this for a couple minutes, and then let me know when you have a question.
So for H2O, like the compounds, would I multiply or add the molar mass of each individual element?
Sorry, I was muted. That was a really good question. So what we want to do is add, we want to multiply and then add. So like hydrogen, that has a molar mass of 1, but there's 2 of them. So we do 1 times 2 would give us 2. And then we add the molar mass of oxygen, which is 16. Does that make sense?
Yeah.
Okay, great. Okay, if you're still working, that's totally fine. Well, let's do these ones together. So N2, do this one down here. So again, we know from the periodic table that nitrogen is going to be 14.01. And there's two of them. So 14.01 times 2. So times this by 2. And we get 28.02. And the units for molar mass are grams per mole. 28.02 grams per mole. Okay, moving on to H2O. So let's look on the periodic table. So we have two elements. We have hydrogen and oxygen. So what are their individual molar masses? Well, oxygen is right over here. That looks like pretty darn close to 16. A lot of periodic tables just have it as 16. So, and then hydrogen looks like 1.01. So let's write that down on our worksheet. So hydrogen is 1.01 and oxygen is 16.0. Now we're going to times these by the amount. So there's 2 hydrogens in water. So times 2, that gives us 2.02. And then oxygen, there's only 1, so just times 1. And then that's just 16.0. And then we want to add up the total. So we get a total of 18.02. And again, the units are grams per mole. And lastly, we have, I forget what this is. Maybe this is propane, something like that. So we have carbon and we have hydrogen. So carbon on the periodic table, look for carbon. Carbon's over on the right side. So carbon is 12.01. So we have 12.01 times, we have 8 carbons in this molecule. And that comes out to be, does anyone have that? I actually didn't type that one out. And then hydrogen, we have 18 times 1.01. So this one would be 18.18. And then 12.01 times 8, let me see what that is. 12.01 times 8 is 96.08. And then we add these up, and you should get a total of 114.3 grams per mole. So that is how we get the molar mass for different compounds. And it's always going to be the same process for the whole semester. We're just going to look at the periodic table, get the number, and add them all up. What questions do you have on finding molar mass? Okay, so let's move on then. And we're going to talk about some empirical formulas and then getting into some actual stoichiometry calculations 5, 6, and 7. Now, an empirical formula is, the way I like to think of an empirical formula is sort of like the simplest version of a formula or the simplest ratio of atoms. So these, I guess the best way to learn is by example. So the empirical formula for H2O2 would just be HO. Do you see how both of these have 2 here? Well, we can divide these both by 2 and you just get HO. You're sort of simplifying it down to the lowest ratio of atoms. So you could have another one that was like C3H6. Well, you could simplify this one down. You see there's 2 hydrogens for each carbon. So the empirical formula for this one would just be C1H2. That is, there's one carbon for every 2 hydrogens. So the empirical formula is just, we're simplifying it down. So why don't I give you 1 minute and try to do B and C here, and then we'll come back together. All right, so let's see which the empirical formula are for these. I should mention something. The ones that I'm giving you here, these are molecular formulas. Molecular formulas. So there's a molecular, which is like the complex version, and then empirical is like the simplified version. So this one here, it looks like we can divide both of these numbers by 2, and we can get N2O5. So for every 2 nitrogens, there's 5 oxygens. So this would be the empirical formula. And for this last one, it looks like this one we can simplify down by dividing everything by 2 also. So we get C2H3 O2N. So it's the same ratio of atoms. And that's all for finding empirical formulas. What questions do you have on number 4? Okay, so let's get on to some actually stoichiometry calculations. Now, let me scroll over here. Now there's sort of this like pathway that we have to take. And if we want to go from different states. So there's 3 things we're going to be dealing with. That is, we're going to have grams, moles, and atoms and molecules. So there's 3 states. We can either have the number of grams, the number of moles, or the number of atoms and molecules. And we can go back and forth between these using our molar mass and Avogadro's number. So if you want to go between moles and grams, this is where we use molar mass. Moles and grams, we use molar mass. And remember, this is measured in grams per mole. So this is where we're using the molar mass from the periodic table. And if we want to go from moles to atoms or molecules, this is where we use Avogadro's number. Avogadro's number. And if you remember this is 6.02 times 10 to the 23rd. 6.02 times 10 to the 23rd. So if I were you, I would write this down on your notes or take a picture. So when you're going between grams, moles, and atoms and molecules, you always have to follow this track. There's no way to go from grams to atoms. You have to go through moles first. And if you want to go between, for example, grams and moles, you have to use the molar mass to do so. It's the only way. Similarly, if you want to go from moles to atoms, we have to use Avogadro's number. So make sure you have this written down or take a picture, because I'm going to move over to the left a little bit again in just a second. And I hope this kind of helps understand a little bit more about where do we use molar mass and where do we use Avogadro's number. So let's apply this to number 5, and then maybe I'll let you guys try to work on 6 and 7. Number 5 says, how much mass in grams is 12 moles of carbon? Well, let's go back over here. We have moles and we want grams. That means we have to use grams per mole. So let's write down, do green. Okay, let's write down what we have. We have 12 moles of carbon. And I always draw out a bar like this, a stoichiometry bar. Now, how can we get from moles to grams? Well, again, to get from moles to grams, we use the molar mass. And what is the molar mass of carbon? Well, we did that just earlier by looking at the periodic table. The molar mass of carbon is 12.01 grams per mole. So we're going to use that here. So 12.01 grams of carbon per 1 mole of carbon. So 12.01 grams per mole of carbon. Now I put the moles of carbon on bottom so that the moles on top cancels with the moles on bottom. That's the rule with these stoichiometry calculations, is 1 unit on top has to cancel with 1 unit on the bottom. And when they cancel, look what we have left. We have grams of carbon left. Now to do this calculation, what you have to do is multiply the numbers on the top and divide the numbers on the bottom. So that would be 12 times 12 divided by 1. And I recommend you try to do this in your own calculator. I know this one's kind of easy, 12 times 12, but they'll get increasingly more complex. So that comes out to be 144 grams of carbon. So just to recap, we put 12 moles, that's what we started with. The molar mass of carbon was 12. So we multiplied those and got 144. Okay, let me start you off on number 6, and then I'll let you work on number 6 and 7 for a few minutes on your own. So again, 198, write down what you have, grams of magnesium, and we want to go to moles. So we have grams here. So we want to put grams on the bottom here. So grams of magnesium. And we want to go to moles. We want to get to moles. So we say moles of magnesium on top. So I'm going to let you guys go from here. So try to find what would you put here, and try to compare it to what we did up here. Try to figure out what you would put here. And then for number 7, I'm not giving you any help yet, but try to work on 6 and 7 for a few minutes, and then let me know when you have a question. Okay, so if you're still working, that's completely fine. This is brand new, so don't expect to be proficient at it right away. So number 6, how many moles are in 198 grams of magnesium? So again, we start by writing what we have in the top left, drawing out a line and dividing them with vertical lines like this, just like it was a unit conversion. And then we say, well, how many grams are in 1 mole? Well, let's go to your periodic table, and magnesium is on the left, so 24.31, we can call it. So just grabbing the number from here, and I forgot what it was already, 24.31, 24.31 grams of magnesium. And what goes on top? Well, just 1. That's the definition of molar mass. How many grams per 1 mole? So all you have to do now is do 198 times 1, divide by 24.3, and that should come out to be 8.14 is what I got. 8.14 moles of magnesium. I'm trying to get better at doing sig figs. I always forget about it, but so the problem here had 3 sig figs, so we should have 3 sig figs in our answer. Okay, and moving on, number 7. So how many molecules are there in 74 grams of carbon dioxide? So let's write down what we have, 74 grams CO2.
I have a question about 5 then. Would we have to have
Yep.
our answer in 2 sig figs?
Okay, great question. Thank you for mentioning that. I didn't bring this one up. So the question was, how many sig figs should our answer here have? So what you want to do is look at the problem. And this has 12.0. Now 12.0 is 3 sig figs. So you count the 1 and the 2, and then after the decimal we have a 0. And the reason that one is significant is because that's like a level of precision. Like we know down to the 10th place how many moles there are. So this is 3 sig figs. Therefore, our answer is 3 sig figs, so 144. Did that answer your question?
Yes, it did. Thank you.
Great. Okay, so let's do so we got 74 grams of carbon dioxide. So let's look back over here at our pathway. We can't go from grams to molecules. We have to go from grams to moles, then from moles to molecules. So we're going to have an extra step in this one. So we're still going to want to put grams of CO2 on bottom and moles of CO2 on top. And why did I put grams on bottom? Because we want to have this grams on top. We want to have the grams on top cancel with 1 on the bottom. So remember, 1 on top cancels 1 on bottom. And so how many grams are in 1 mole of carbon dioxide? Well, we have to look at the periodic table for this one. So we have carbon, which is 12.01, and oxygen, which is 16. So just like we did the molar mass above, we're going to add up the molar mass for this one, which would be 12.01 plus 16, which is for oxygen, times 2. So we have 1 carbon, which is 12, plus 2 oxygens, each with a mass of 16. And this will give us a molar mass of 44.01 grams per mole. So we're going to put the molar mass of carbon dioxide right down here, 44.01 grams. Just let me know when you're losing me, and I can answer your question. Okay, so we get rid of grams, and now we're at moles. So now we want to go from moles to molecules. So moles of CO2 we're going to put on bottom so that it cancels with the one on top. And then we want to put molecules of CO2 on top. We always put on top what we want to get to. We want to get rid of moles and go to molecules. So again, look here. We have moles of CO2 on top and moles of CO2 on bottom. That cancels. Now, what is this conversion factor, 1 mole to molecules? Well, this is where we're going to use Avogadro's number. It's always going to be the same, 6.02 times 10 to the 23rd. So 1 mole, 6.02 times 10 to the 23rd molecules of CO2. So we are done now. We only have molecules of CO2 left on top, and now it's just a calculation. So what you're going to want to do, and I'm sorry again, I wish I had a calculator to show you guys like in person, but we want to do 72 times 6.02 times 10 to the 23rd divided by 44.01. And I would recommend trying that in a calculator and see if you can get the right answer, because sometimes the hardest part of these is typing in your calculator. And I get an answer of 1.0 times 10 to the 24 molecules of carbon dioxide. And just for sig figs, so this one here has 2 sig figs. So this answer here should have 2 sig figs. 1.0 is 2 sig figs. What questions do you have on numbers 5, 6, and 7?
Question about like the conversion from moles to molecules and atoms.
Yep.
So is atoms and molecules just the same thing then if you just times it by Avogadro's number every time, or like what's the difference?
Yeah, great.
Atoms or molecules?
Yeah, great question, Ryan. So Ryan was asking, well, so when you say over here you can go moles to atoms and molecules, which one is it? Is it atoms or molecules? The answer is it depends. It depends what you're dealing with. Here we're dealing with carbon dioxide, which is a molecule. Therefore, our answer will be in molecules. If this was just a single atom, then our answer would be in atoms. Does that make sense a little bit, Ryan?
Yeah.
Okay.
Thanks.
So there is a way, like let's say that the question wanted to say how many oxygen atoms are there? Well, then what we would have to do is take our answer here. If we wanted to find oxygen atoms, we would have to times this by 2. Does anyone know why we would times it by 2 if we were trying to get oxygen atoms? So we would times, if we want to get oxygen atoms, we times it by 2 because for each molecule of carbon dioxide, there's 2 oxygen atoms. So in each molecule, there's 2 oxygens, and this would give us 2.0 times 10 to the 24 oxygen atoms. So Avogadro's number, to summarize, you can go to molecules and atoms. You just kind of have to be careful about what you're doing your calculations with. Is it a molecule or is an atom? What other questions can I answer about these ones? Okay, so and we're going to do a bunch more practice for the next 2 weeks. So if this is still kind of blurry to you, that's completely normal. So we're going to finish up on number 8 today, and then number 9 we can get to on Wednesday. So the last topic today is percent composition by mass. So a percent composition by mass is saying if you have some sort of a compound, what percent of the mass is made up by hydrogen, for example, and what percent of the mass is made up by oxygen. So let me do an example, and then I'll let you do a couple on your own. So what we want to do I guess I can write the general formula. So the percent is going to be the mass of, I'll just call it A, whatever element you're interested in, divided by the total mass, or the molar mass of that element, or the molar mass of the molecule, times 100. And times 100 turns it into a percentage. So what we have to do is figure out what is the mass of each element here. Well, we have 2 hydrogens, and each of them are a molar mass of 1.01. So that means the mass of the hydrogen in water would be 2.02. And the mass of oxygen, well, we have 1 oxygen times the mass of oxygen, which is 16. So again, from the periodic table, is 16. That would give us 16.0 for oxygen. Now to add up the total mass, that would be 18.02. And since we're dealing with molar mass, it's probably a good idea to toss on grams per mole. So step 1 is get the mass of each element. Step 2, find the mass of the total mass, which we found. Step 3 is finding the percent. So the percent of hydrogen is going to be, following the formula, the mass of A, or whatever you're looking for. So in this case, hydrogen. So mass of hydrogen, 2.02, divided by the total mass, which is 18.02, times 100. And if you do 2 divided by 18 times 100, you should get, let's see, 11.2%. And this one didn't have any sig figs, so let's shoot for 3 sig figs on this one. And then for mass of, or percent of oxygen, again, we do the mass of oxygen, which we found was 16, divided by the total, which is 18.02, times 100. And that should get you, let's see, 88.8. And you know you did the problem right if your total percentages add up to 100, because that just makes sense. Okay, so why don't I give you guys a few minutes and try to work on CO2 and methanol, or propanol, and then we'll come back together in a few minutes. Okay, so I know you guys are still working on these, but just for the sake of time, I'll try to get you answers for these ones. So moving on to this one, so carbon, we have one carbon, the mass is 12.01. So that's 12.01 for carbon. Oxygen, looks like we have two oxygens and CO2, each with a mass from the periodic table of 16. That gives us 32 for oxygen. So adding up a total, that looks like 44.01. So then if we want to do the percent of each one, so percent carbon is going to be 12.01 divided by 44.01 times 100. And that comes out to be, looks like 27.3. 27.3%. And then percent oxygen is 32 divided by 44.01 times 100. And that comes out to be, if we did it right, it should be the remainder of 100%, 72.7%. And I just did these about an hour ago. So if you have a dispute or you think I missed something, it's totally possible I could have missed something. Just let me know. And then lastly, C3H8O, this is propanol. So for carbon, once again, we're going to find with 3 carbons times a molar mass of 12.01. That gives us 36.03. For hydrogen, we have 8 hydrogens times 1.01. That will give us 8.08. And then oxygen, we have 1 oxygen times 16, which is just 16. So adding those up, you should get 60.11 for the total molar mass. And then to get the percent of carbon, so again, we're just going to divide these two. We have 36.03 divided by the total, 60.11 times 100, so it goes to percent. And that comes out to 60.0. If you guys are slightly off, that's fine. I'm mostly going for the making sure you guys know how to do it. If you're off by a few decimal places, that's fine. Hydrogen, we have 8.08 divided by 60.11. That is, let's see, 13.4%. And then the percent oxygen is 16.0 divided by 60.11. And that comes out to, I got 26.6. But again, if you're pretty close, that's fine. Okay, so lastly, what I would recommend you do whenever you finish these problems is just check, does this add up to 100? If you did, you can be pretty certain you did it right. If it doesn't add up to 100, you know for a fact you did it wrong. So what questions do you guys have on percent composition by mass? All right, so we will stop here for today. On Wednesday, so Wednesday is at 4:30. We're going to continue on and do a little bit more complex stoichiometry and mole calculations and stuff. If you guys have any questions, feel free to stick around for the next few minutes. Otherwise, we'll see you guys on Wednesday.
Thank you.
You're welcome.